Good afternoon. My name is Ricky. I represent Ultipa. What the talk is about the paper that we published last Sunday, or this Sunday, on the 18th. Today I'm going to just go through the whole paper very quickly because I think I have too much information. I probably need to comprise everything to within 15 minutes. Well, this is about design of highly scalable graph database systems without exponential performance degradation. So now let's take a look at from single instance. That's how we started building a graph database system, and eventually all the way to be horizontally scalable, right? Standalone, master slave, high availability, disaster recovery, and distributed consensus, and to be like which is Raft, and to go truly enterprise ready. We probably will call it something like HTAP and proxy. Some vendors call it like federation, or using a lot of name servers and meta servers. And the ultimate form of distributed graph database system is automated sharding, right? But as you can see, as we are evolving, so we want a system to have better stability and also a lot more storage, capacity. And we do a lot of integration and sharding. The whole process is very much like, if you think about the topology of the system structure, we're really going from node, single node, multiple nodes, to tree in terms of topology, and also to a genuine graph. So today I'm going to spend more time on sharding. Well, this is the thing that when we talk about scalability, normally we only talk about volume. We want just so much more volume, but we forgot about the depth. For graph system, if we don't deeply penetrate, we don't concern the depth, we're not building graph systems. We can just building any kind of, NoSQL systems that we can store, just like a big data Hadoop, unlimited storage capacity, but it definitely doesn't have the capacity to deeply penetrate, to deeply correlate, to deeply traverse large amount of data. So if we look at RDF stores, like RDF stores are not known for that ability to deeply penetrate. We also have non-native and native graph stores, and we also have, academic-focused graph computing frameworks. Where normally they can do so much deeper by using, like in-memory computing, a lot of optimization techniques. But I think that the key thing, maybe down the road for the multiple, like decades, I don't know for how long, like we should talk about how we can make native graph stores to be truly scalable, in the first quadrant. The ability to process ultra large amount of data, volume, and also to be able to deeply penetrate. And ideally in real time or near real time. That's our ultimate goal, right? So today we're going to talk about that. We are all pretty familiar with the K-hop, right? I mean the Twitter 2010 dataset. It has like 42 million vertices and almost 1.5 billion edges. No matter what kind of architecture you have, well, that's the benchmark that we documented. Because the Twitter dataset has a lot of supernode, hotspot supernodes, right? And even one hop can be pretty challenging for some graph databases. As you can see, the timing, the latency is in second. And the second hop, for instance, like you can see a RunGo Genus graph, they're going to take like half minute. For 3 hop, so a lot of things going to run in pretty much in batch processing. They're going to take hours, right, to process it. And 6 hop, pretty much like traversing the entire graph site, or the graph data set. Other system would time out. And this is what we did. Like I think I did this on Monday morning. starting from, ID 12, that's a supernode. So traversing for 6 hops from 1 to 6, it took us 1.7, almost 1.7 seconds. And the neighbors, counting all the neighbors from the first all the way to the 6th hop, we have almost 42 million. That means we are basically traversing the entire data set, meaning on average, we're pretty much traversing 1.5 billion, edges, nodes and edges in 1.5 seconds. So it's just 1 billion per second. We can't achieve this kind of speed without high density parallel processing. And if you are doing that in a truly scalable, horizontally scalable architecture, you're not able to achieve this kind of performance because we're talking about deep traversal. You probably can achieve that with 1 hop, but not 6 hop. So the 3 architectures that we proposed in the paper, the testing, that performance was only achieved on the HTAP architecture. The pros and cons, high performance, and the cons is that we can only do vertical scalability. Horizontal scalability is a big problem. That has to be handled by the second and third schools of design. So the second is, the key differences between the second school and the third school are really about, are we using human intelligence to partition or to shard the graph data set? We all wanted to, to achieve, without knowing any business details, so that we can fully, automatically sharding everything. That is not possible. Based on many years of industrial experience, I don't think any system can handle that kind of sharding, just bluntly, because sharding is an NP-hard problem. So in industry scenarios, we actually using non-transparent graph partitioning, meaning human logic, based on, we do know certain data can be put together in one graph and the other data would need to be in separate graphs. So the partitioning logic has human involvement. Automated sharding sometimes can be, great, but most of the other times the performance is not good at all. But we can potentially integrate, all 3 schools of design in one. That is that is how we are, partitioning things, per business scenarios on the right-hand side, which we listed, if it's online fraud detection and you need high density parallel graph computing capacity, and you probably don't want to partition the data too much. If you partition too much, you're not able to achieve real-timeness. We're not talking about, I think the last presenter talked about half second. We have seen bank asking us to do things within 10 or 20 milliseconds per transaction. And consider we have thousands of transactions flowing in every single second. That's how the industry is handling real-time data processing. And within that 10 milliseconds, I'm sorry, I'm talking about millisecond. Within that 10 milliseconds, you need to process maybe 10 or 20 graph models, deeply penetrate the data, looking at the transacting party's neighborhood. So that can be quite a challenge, which means every single model has to be executed in terms of hundreds of microseconds. We're not talking about even millisecond, we're talking about microsecond. So, but there are many other scenarios, which is very much like data warehousing or data science. They can wait. That means we can process data in a batch processing way, very much like Hadoop days, so things can go very slowly, T+1 fashion. There are just so many scenarios. It's pretty much impossible using one simplistic architecture, one unified homogeneous architecture to handle all the scenarios. That's what we learned over the years, right? So this is how we when we are trying to build a really, sophisticated sharded architecture, we need to have name server, meta server, and also shard or peering server. And also we need to involve elastic computing node. That is to aid by dynamically allowing us to allocate, computing resources. Let me give you one example. When we are trying to do K-hop, how are we going to parallelize the whole execution? Assuming we are doing K-hop against 4 entities, 4 vertices, so they are actually can be distributed onto CN1, 2, 3 are the 3 computing nodes. So things can be load balanced among these available computing resources. That's pretty straightforward. The tricky part, taking the path from let's see, we're trying to find out the shortest path between the 2 entities, A and B. There are 3 categories of scenarios. Number 1 is everything is actually co-located on computing node 1. That is very straightforward, right? There's no data migration needed. And the second scenario is that partial computing can be done on computing node 1 and 2 separately, individually, and eventually there will be some kind of data aggregation happening potentially on name server or with dynamic computing node. The third scenario is actually more complicated, which means in the worst case, all data will need to be migrated from computing node 1 all the way to computing node 2. So that means even before you can achieve anything or compute anything, a lot of it, you have to wait. So this is the worst scenario, but that happens occasionally. All we need to do is that when we are trying to partitioning data, we should try to avoid the third category of scenarios, because that's a disaster. That means things can run super, super slow. Essentially, if you look at the shard cluster architecture, the hierarchy is very much like a graph. So we're using graph to manage graph. And in our latest, in the Ultipa version 5.0, so we are doing multiple things to summarize. With type 1, data processed on name servers. So this is not so much different from Hadoop setup from 20 years ago, right? And type 2, this is something new, right? Data processed on shard servers and name servers. We're using a peer-to-peer architecture. And also, very much like traditional, on relational database, the peculiar part about building a distributed graph system is that we need to use the exchange operator to separate the relational data streams and graph algorithm data streams. And also there are optimizations for relational data flow, and also in terms of figure out when we are trying to do graph queries, the range, we need to set up restrictions. So that's the tricky part to really make a graph queries flow. And we have done some, very early findings. As you can see, for a scalable, highly scalable system, graph system, the only benefits we can see that online data ingestion, by using only 3 shard, we pretty much achieve like a 300% plus performance improvement in terms of online data ingestion. But look at everything else. Look at all the deep processing, data processing things like K-hop, 3-hop. Pretty much the sharded setup is 15 times slower. And for the shortest path, that's another also 15 times slower. For PageRank, which is the simplest form of a graph algorithm, we're 10 times slower. LPA 15 times. And Luwen, we haven't really done Luwen because we really don't know how to make Luwen run on a truly scalable distributed system. I think that warrants another paper that we're going to talk about, because I think right now Luwen has to be centrally computed to ensure the correctness of the results. All right, so to summarize the 3 schools of design, HTAP, proxy, and shard. Okay. Well, thank you for listening.
Thank you. Question from me right away. So the 6-hop result that you showed, was it on a distributed setup or a single machine?
It's a distributed setup.
Yeah. How many instances?
For HTAP, that's, can start with the 3 instances. For proxy, it has to be like, I think in real world deployment, we have like 12 or 15 instances, because there are many, management node name servers. And for shard, similar. We have like management nodes, shard nodes, computing and storage nodes, and also meta servers. And, that's just to make things so much more complicated.
Right. Thank you. Any more questions, Wim? Yes, please. Walk here.
Hello. Hi, this is probably just going to be a small detail, but in the beginning of the talk, you mentioned some numbers about a Facebook data set, and then
the Twitter.
Yes. It was Twitter. Okay.
It was Twitter, yes.
Do you have an idea of how many nodes and edges the graphs has, like roughly?
Well, on average, there are 42 million nodes and 1.5 billion edges.
Okay.
Well, which is considered a reasonable sized graph.
Yeah. Okay.
If we're pushing the limit to, multi-billion or 100 billion, I mean, there's no way you can store on one machine.
Yeah.
But then everything will just be running so much slower.
Okay. Thank you.